Hello everyone. Today I am presenting our work, FlakeFlagger, predicting flakiness without rerunning tests. My name is Abdurrahman, and this work in collaboration with Chris, Michael, and Jonathan. So let's see first what a flaky test means. When a test gives two different outcomes, pass and fail, without any change to the code, the test is flaky. Let's see the following example to understand how a test can be flaky. This example schedules a task as shown on line 5 to run, and once it is completed, the value of I should be changed to 1. The test will fail when the task on line 5 completes the execution before line 9. The test will pass when the task on line 5 is completed after line 9 is completed and before line 11 is reached. So this is a simple async flaky test as discussed by Lam et al. Async wait is one of the root causes of flaky tests. In the pie chart, Leo et al. Discuss 8 different causes of flaky tests. Please refer to their paper for further details. So, flaky tests are a problem in software testing because they are hard to identify. The traditional way to detect flaky tests is to rerun them multiple times. Besides the rerun technique, deflagger is another approach to detect flaky tests using code coverage. Predicting flaky tests before running them is a promising technique because detecting approaches require tests to be rerun many times. Another problem of flaky test is how to determine if a failed test is because of flakiness or regression. Even if the test is confirmed as a flaky, it is not easy to tell from logs what may cause the flakiness. In this work, we will focus on predicting flaky tests. Our main goal is to create a new approach to identify which tests in a test suite are flaky without rerunning them multiple times. In order to build and evaluate a flaky test predictor, we first needed to construct a rich dataset of flaky tests, which is one of the main contributions of this work. This dataset is a result of running 24 different Java projects 10,000 times. From left to right, each project name is followed by the number of tests that we were able to run, then followed by the number of flaky tests we detect. In the following two columns, we show the common flaky tests we detect compared to two known datasets that study the same version of the same test. From this table, we can see how it is hard to reproduce the flaky test by only detecting 22 out of 52 previous non-flaky tests from ID flakies, even after rerunning them 10,000 times. In this table, we categorize the observed flaky test by percentage of flaky tests detectable after 10, 100, and 1,000 runs. In the last column, we present the failure frequency of the flaky test in 4 different sets. For example, if a flaky test fails less than 10 times out of 10,000 times, the test should be in the red bar. This is also an indicator that it is hard to tell how many runs we need to observe flaky tests. We did this experiment at a certain time and a specific run environment, and replicating our experiment may not have the same number of flaky tests or even the same flaky test distribution for a specific number of runs. This is a full result of 24 different projects as we find 811 flaky tests. You can find more details about our empirical rerun study in our paper. In this work, we propose a FlakeFlagger, a tool that predicts flaky tests. FlakeFlagger is represented as a classification problem when the tool learns from existing flaky tests in order to predict the other tests. FlakeFlagger has 3 main components. First, it has to have a dataset of flaky and non-flaky tests to learn from. In our case, this source of flaky test comes from our rerun result. The second phase is called feature collection phase, where we run each test one time to collect our implemented features. Then we apply the supervised learning algorithms to predict flaky tests. This classification problem will result in what is called the confusion matrix, where we can evaluate FlakeFlagger. I will discuss only the feature collection phase in this presentation. In the feature collection phase, we develop a set of features that we believe they can be predictive for flakiness. As shown in the table, we have listed different test smells and other numeric features. The idea is that we represent each test as a row of values based on these features to be used in flakiness prediction. The result of this phase is a set of 16 features. FlakeFlagger features are based on dynamic analysis, and the collector is an extension to the Maven build system. Basically, we collect the statement coverage of each test. From that, we implement the logic of each feature to be able to extract their values. We evaluate the efficacy of the FlakeFlagger prediction result as one part of our paper evaluation. We omit this presentation to discuss only this research question. Please refer to the paper for full research questions evaluation. In this part, we apply the state-of-the-art prediction approach presented by Bento et al. On our rerun dataset. This approach simply relies on the content of each test by collecting the tokens and Java keywords and using them as predictive features. We think that if we can collect more than just static features, such as execution time, we might have better prediction rate. In this work, we measure how well each approach is in terms of prediction flakiness. We did this by applying the state-of-the-art approach and FlakeFlagger on the same dataset. As a result, we evaluate the performance of FlakeFlagger and the state-of-the-art by collecting the confusion matrix, precision, recall, and F1 scores. From the table, we can see that both approaches have very good rates in terms of how many flaky tests have been predicted correctly. We mean the true positive values. We also observe that FlakeFlagger has very low number of false positive, which are tests that are predicted as a flaky while they are not, based on at least our rerun result. The low number of false positives help researchers to minimize the number of tests which may have top priority to investigate in terms whether they are flaky or not. We investigated more on how the true positive rates are distributed by project. We found that FlakeFlagger outperformed on 16 of the 24 projects and tied on 4 projects. FlakeFlagger has some limitations. We know that the projects from our rerun may not be representative of all Java projects, so we cannot generalize the conclusion of FlakeFlagger on all other projects. Also, we cannot guarantee that we capture the likelihood of flakiness. We also found that the dataset used in flakiness prediction is not perfect in terms of capturing all flaky tests in particular project, as proven in our rerun result. The main point of rerun is to confirm a test as a flaky if it passes and fails, and cannot confirm if the other tests are not flaky. We have not changed the order of tests during the rerun. This means at least we didn't capture flaky tests caused by test order dependency. Even if the idea of this work is applicable on many different languages or other Java projects, FlakeFlagger works only on Java projects which can be run by Maven. In the conclusion, we showed that rerunning tests many times may not be practical because it is expensive. So we try to help by proposing FlakeFlagger, which is a tool that predicts which tests in a test suite have flakiness without the need to rerun them. This work has 2 main contributions. First, we provide a rich flaky test dataset, which hopefully helps researchers who study test flakiness. Second, we propose a feature collector and flaky test predictor. In the FlakeFlagger evaluation, we showed that FlakeFlagger outperformed the state-of-the-art approach by F1 score. We are working to improve the current work and flaky test prediction in general. Before I end this presentation, I would like to thank Paul Amen, Darko Marinov, and Wing Lam for their discussion on flaky test. Thank you for listening.
Hi everyone, welcome back. We have now the authors of the second paper in the session, Abdul and John, here in the session, ready to answer your questions. The paper is titled, as you've seen already, FlakeFlagger, Predicting Flakiness Without Rerunning Tests. This is part of the technical tracking ICSE. So we already have a couple of questions, and I will start there. One question from Darko. Hi, Darko. How can we get your model to try it out on other tests?
Yes, I think we have offline discussion with Darko Marino about applying FlakeFlagger on other tests. So we published that one on GitHub. So there is one way to apply FlakeFlagger on any other test. So that one, what we need here is just to collect the features that we did in the test collector of FlakeFlagger.
We have a very nice question from Michael as well. Do you have any insight from your study on which of the 16 features are most useful to make accurate predictions?
In the content of our dataset, we found that execution time has the most influence part, plus other dynamic features. We have to be careful on generalize that conclusion on other tests, because we found that our dataset cannot generalize the likelihood of flakiness. So I have to be careful on that conclusion. But in the content of our dataset, we have found more dynamic features that have more influence in terms of the information gain we get from that one.
Great, thank you very much. Bram is asking basically the key question that I had in my bag. So of course you have that rerunning test cases require some effort and you want to avoid that, but on the other hand, your model is not perfect, right? So how about a hybrid approach where you use a model to reduce the rerunning or somehow combine the two strategies? I think this is mentioned at some point in the paper as well, if I'm not mistaken.
Yes, I think one of the takeout of the FlakeFlagger is to give a priority of which test can be or have the top priority to have it in the rerun. And this is what we call the false positives test cases that resulted from FlakeFlagger. Prediction, as you know, it's not 100% sure about that one, because there are many hidden factors, like the data set that we train on, the list of features that we build the model based on that one. So we try to give, like, one of the use cases of FlakeFlagger is to at least minimize the number of flaky tests or suspicious flaky tests to if a developer want to rerun them multiple times. If you have to decide to join about this point.
Thank you very much. Welcome, Michael. We have another author of the paper here as a backup. We have a question from Jane McIntosh. He's asking, did any of the supervised classification approaches that you use tend to outperform the others? Should any approaches be excluded from future studies?
We apply just the multiple supervised learning algorithm, but most of the related study of prediction flakiness use the random forest. We cannot make sure that a specific supervised learning algorithm should be excluded, because we just hit the ground about the prediction of flakiness. So I would say I recommend the random forest over the other things, based on not even the FlakeFlagger studies, but even other the flakiness prediction.
Great, thank you very much. We have a question from Chanduk Ngo. Do you think the set of features could be applied to other languages besides Java?
The idea is applicable on that one. So one of the limitation of sorry for the noises. One of the limitation of our work is that the feature collector is based on Maven and as an extension of Maven. So the idea is applicable on other languages like Python or any other languages. The idea, it seems like applicable, but we haven't tried on other language. So this is one of our future work.
Thank you. We have a question from Martin Gruber. Do your training and test sets share tests from the same project, or do you use completely different projects for testing?
What we have tried is the stratified cross-validation. The cross-validation is to get an equal portion from each project for testing and the remaining for training. So we don't train on, let's say, one project and test on another project. We train on 80% of the test in project A plus 80% of project B and so on. And we test on the remaining test on that one.
Great. Thank you very much. Marcelo Damorim. Hi, Marcelo. Did you try existing tools for test smell detection or implemented your own?
We start implemented the test smell detection from our own, not because that we really appreciate the other existing smell detection. And this is one of the discussion with John that we have about using existing one. But we just come up with extending our work by even provided another smell detection for that one.
I'll just jump in quick. The very key difference in our test smell detection versus prior work. I think that most test smell detectors previously statically examine the test method bodies in order to attribute a specific smell to a specific test. The kinds of tests that we were looking at, which are flaky, are usually much larger tests, getting a lot closer to an integration test than a unit test. So you'd end up missing out on a lot of what's actually happening in the test. So we have a hybrid static dynamic test smell detector that first executes each test, collects the coverage to see which statements are covered, and then we examine all of the covered statements for each test for the presence of smells.
Great, thanks. Tien has a question, and he basically asks you to conjecture on why conditional logic as a feature doesn't have much impact in the prediction of flakiness, which seems a bit counterintuitive.
Yeah, I mean, in the content of our dataset, we might not see that specific feature as a high impactor or indicator for flakiness, but that doesn't conclude that it will not be the same on other projects or other studies or application for FlakeFlagger. But we don't have a clear insight on why some feature like the conditional logic have very low one, because we have some limitation in terms of the flaky test of in our dataset, that even maybe some other flaky tests that are not revealed with our rerun. So all these limitations limit us to just give some insight. What we try to do is to give a way to evaluate each feature by information gain scalability.
Thank you very much, Abdul. Excellent timing, actually. Thanks, Abdul. Thanks, John. Thanks, Michael. Very nice work. Really interesting presentation as well. And for the rest of the audience, the next paper is on flakiness in UI. So also very interesting work. And I'll see you all in 10 minutes for the Q&A of that paper. Thank you all very much.